So, this is our question. A particle of mass m moves in a circular orbit under the force Fr equal to minus Kr. You know what kind of force is this? You can have a spring attached to mass and so on in that Kleppner book. That figure is given where spring is attached with the mass, and this kind of force is applied with a total energy u naught. So, total energy u naught is given. Find the radius, the speed and the angular momentum of the particle. So, let us go one by one. So, the first part is find the radius, speed and angular momentum. So, once again we can use our knowledge of circular motion. Force is Kr towards the center, that should be equal to m times v square by r. So, this is one equation. So, m v square is equal to Kr square. We have to get the speed as well as the radius. So, two unknowns are there, but then the total energy is given u. The total energy u naught is equal to half m v square kinetic energy and potential energy. If Fr is, if F is minus Kr, you very well know it is half Kr square. Okay, it is half Kr square. If you differentiate and put a minus sign, you will get force. So, plus half Kr square. So, these are the two equations and you have two unknowns. To get mv square, you can write this, you can use this, u naught is equal to half mv square and plus half Kr square, which is again mv square. So, which is m times v square, and therefore, v is equal to square root of m u naught divided by m, u naught divided by m. So, that is the speed, and radius you can obtain from anywhere. So, r square is equal to, or here itself for radius we write u naught is equal to half Kr square plus Kr square half. So, this is equal to Kr square and r is equal to square root of u naught by k. So, that is the radius, and angular momentum, if it is going in a circle, and angular momentum means obviously angular momentum about the center of this circle. So, if this is the circle, if this is the radius and if this is the velocity, if it is going in circle, the velocity has to be in tangential direction, and therefore, L will be just m times v times r, and that will be m square root of u naught by m and into u naught by k, m into v into r. So, this is v, this is r. So, it is this. Okay, this will be square root of m square goes here. So, m here, u naught square here and by k here. So, that is the first part. Right, mass into speed is square root of u naught by m and r is square root of u naught by k, and therefore, it is under root m u naught square divided by k. Now, a sharp blow is given to the particle in the radial direction, so that it achieves a small radial speed v. So, the particle is going here with this speed v, which is written here, and then it is given a sharp blow in this direction, radial direction. A force is applied for a short time in this direction. What will this force do? It will create a velocity in the radial direction, but this tangential velocity will still remain the same, right. So, and that velocity which is achieved here is capital V, that is given. So, that it achieves a small radial speed v. Find the maximum and minimum distance of the particle from the original center. So, originally the particle was at this distance given by this equation, but now that you have given extra energy the particle will not go on circle, but it will remain in the vicinity of the circle. So, we have to find the minimum and maximum distance from the origin. How do we do that? We write now the initial total energy is equal to half m v square, and initial total energy, let me write. So, half v square, this v. So, let me call it v naught square, this v, and plus half m this capital V square, and then the potential energy half k r square. Okay. This is the total energy. Kinetic energy, now I am writing for a general R as such. The kinetic energy initially is, okay, let me write it initially. So, this is the energy. So, initially the velocity is v in this direction, capital V in this direction, and therefore, the kinetic energy will be half m net v square, but that net v square will be this square plus that square. So, that is the kinetic energy, and then the initial potential energy at the time of just before, just after the blow, let us say just after the blow, the kinetic energy is this and potential energy is half k r naught square, where r naught is this is r naught. Alright. So, this is it. We can write the values also. Half m v naught square will be half and then v naught square. So, this will be u naught, correct, half m v naught square. So, m v naught square will be u naught. So, it is this, and then plus half m v square, it is given to us, and then half k r naught square will again be this. So, it is again half u naught, and you have just increased the energy by this half m capital V square. So, this is the energy. What is that effective potential now? V effective, it is L square. Now, I am going for a general R in this motion, L square by 2 m r square, and then plus the potential energy is half k r square, right. After the blow, it is going in some path in xy plane, and in that situation this is the actual potential energy, and L square by 2 m r square is that term which is coming, and then this is the effective potential energy. Plot it. How it will look like? All the time positive. There is a one minimum, never crosses 0, all the time positive. There is one minimum, and therefore, the shape will be of something like this, and here is that u naught. Here is that u naught. If the energy is u naught, it is going in the circle. So, it has to be this lowest point where you have only one value of r possible, and that is r naught, right. But now, the energy is more. Now, the energy is more. So, energy is here. This is the energy, and therefore, you have two turning points, r1 and r2. This is r1, which is the minimum distance from the origin, and this is r2, which is the maximum distance from the origin. We are asked to obtain this r1 and r2, and you know that here this u is equal to value of this effective potential energy, that is L square by 2 m r1 square, and plus half k r1 square. And here the same equation, L square divided by 2 m r2 square and plus half k r2 square. So, now you have the equation. So, essentially what is it? It is u is equal to L square by 2 m r square and plus half k r square. It is this equation which will give you two values of r, one will be r1, one will be r2, and now you can write. So, it is u naught is original. So, now you can write the values also, you are given what is u naught and all that. So, it will be u naught plus half m capital V square is equal to L square by 2 m r square and plus half k r square. Okay. So, multiply by r square, if you so wish, you will have half k r to the power 4, this term here, then take this whole thing on that side, it is u naught plus half m capital V square and into r square. So, we are multiplying the entire equation by r square and collecting on one side. So, this into r square goes to the right, and then you have this term here plus L square by 2 m, right, is equal to 0. So, everything is there, k is there, k is 3 in SI units, then u naught is there, this is 12 joules, mass is there 2 kg, and this mass is given L square you have already calculated. What is L square? Here is L square, that is also known. And remember, in the radial blow L has not changed. Okay. Since the blow was in radial direction, this component, when you write angular momentum r cross p or m times r cross v, this component will not give you any contribution and the angular momentum is still there. So, this original angular momentum that we had calculated can be obtained from, can be put there. So, it is a quadratic equation. It is a quadratic equation and you find the two values using your class 9 algebra, and the two values of r square you will obtain and then take the positive square roots, those will be r min and r max. So, if you do it correctly, you should get r min and r max, which are root 8 by 3 and root 6 meters. Okay. So, that is how you can get these values.